In this video series subset, we're examining 3 different hydrogen pathways in the HDSAM model. In the first 2 videos, we looked at liquid hydrogen and compressed hydrogen gas transported via tube trailer. In this third video, we'll look at compressed hydrogen gas transported via pipeline. I'll quickly review the scenario worksheet to identify the relevant selection options for this pathway. I'll step through the structure and inputs of the 3 compressed H2 worksheets, and I'll compare different hydrogen fuel distribution modes with a demonstration. The HDSAM model incorporates economic data into the energy and emissions modeling provided through GREET to enable assessment of financial sustainability as well as environmental sustainability of hydrogen delivery pathways. In HDSAM, the gaseous hydrogen pipeline pathway begins at a centralized gaseous hydrogen production facility, after which the gaseous hydrogen is compressed and transported in a variety of directions using a transmission pipeline. The transmission pipeline can deliver the hydrogen gas to geologic storage or transfer to a distribution pipeline to deliver the gas directly to a refueling station. Alternatively, the transmission pipeline could terminate at a gaseous hydrogen terminal, where the gaseous hydrogen can be compressed and delivered to a refueling station using a tube trailer distribution mode. The transmission pipeline could also terminate at a liquid hydrogen terminal, where the gaseous hydrogen is converted to a liquid fuel and delivered to a refueling station using a liquid truck mode. As I've shown in other videos, on the scenario worksheet, we see the market demand selections, delivery mode selections, a refueling station capacity selection, and storage options. The selections for the pipeline pathway include the pipeline options for the transmission and distribution modes, and geologic gaseous storage for the storage option. At the top of the H2 compressor worksheet are tables showing the calculation outputs from the sheet, as well as energy use and emissions resulting from the process. The primary outputs in these tables are the compressor portion of the real levelized delivered hydrogen cost, which is made up of contributions from capital cost, energy and fuel, and other costs. System energy use is another primary output. The first inputs table is for hydrogen compressor design inputs, and some inputs of note in this table are the inlet pressure, the number of backup compressors, the number of compressors in operation at any time, and isentropic compressor efficiency. The second table presents compressor calculations where all value cells are calculated cells. The economic assumptions table comes next. Inputs required in this table are compressor lifetime, state taxes, and federal taxes. Next, there are a couple of tables related to capital investment. In the first such table, there's a value for motor rating per compressor, and the total initial capital investment is reported here. In the second capital investment table are required inputs for land cost, as well as other capital costs that include site preparation, engineering and design, project contingency, one-time licensing fees, upfront permitting costs, owner's costs, and other capital. The table that follows contains O&M costs. The significant inputs here include labor cost, electricity consumption and related cost, insurance, property taxes, licensing and permits, operating, maintenance and repairs, overhead and G&A, and other fixed operating costs. Beyond that are several tables that contain all calculated values. On the gaseous H2 geologic storage worksheet, there are some notes regarding geologic storage that precede the calculation outputs table. The primary outputs in the calculation outputs table are the delivered real levelized hydrogen cost portion from gaseous H2 geologic storage, comprised of the cost contributions from capital, energy and fuel, and other costs, as well as the output of system energy use. In the first inputs table, geologic storage design inputs, inputs of interest include cavern maximum and minimum pressures, number of backup compressors, number of compressors in operation at any time, and isentropic compressor efficiency. The second table for geologic storage scenario inputs has input fields for maximum allowable daily hydrogen withdrawal rate and maximum allowable injection rate. And the next table shows calculated values for geologic storage. The economic assumptions table is where you can specify the compressor lifetime, the cavern lifetime, state taxes, federal taxes, and the cost of hydrogen cushion gas. In the second of the two capital investment tables, there are required inputs for site preparation, engineering and design, project contingency, one-time licensing fees, upfront permitting costs, owner's costs, and other capital. In the O&M costs table, the inputs of interest include labor cost, insurance, property taxes, licensing and permits, operating maintenance and repairs for remainder of the facility, overhead and G&A, and other fixed operating costs. And again, the remaining tables contain all calculated values. On the H2 Pipeline Worksheet, the primary outputs in the calculation outputs table are the pipeline portion of the real levelized delivered hydrogen cost, the broken out cost contributions to the process from capital, energy and fuel, and other costs, as well as system energy use. In the first inputs table for pipeline design inputs, there's a selection related to calculating the pipeline diameter. Other significant inputs are transmission pipeline inlet and outlet pressures, trunk pipeline inlet and outlet pressures, and service pipeline inlet and outlet pressures. The table for scenario inputs has input fields for hydrogen lost during transmission and hydrogen lost during distribution. After the calculated values table is the economic assumptions table, where the significant inputs include the pipeline lifetime, state taxes, and federal taxes. On this worksheet, there are no inputs of note in the capital investment table. In the fixed O&M costs table, the inputs of interest include labor cost, insurance, property taxes, licensing and permits, operating maintenance and repairs, overhead and G&A, and other fixed operating costs. For demonstration, I'll run 3 scenarios showing how results change when selecting the 3 different distribution modes for delivering gaseous hydrogen when the transmission mode is pipeline. In the first scenario, I'll look at results using the tube trailer distribution mode. The pathway represented in this scenario would be gaseous hydrogen transmitted via pipeline to a terminal, where it is transferred to tube trailers to be distributed using trucks. On the scenario worksheet, I'll select urban as the hydrogen market and choose Sacramento as the city selection. I'll set the hydrogen vehicle market penetration at 4%. I'll select the transmission mode to be pipeline and the distribution mode to be tube trailer. The dispensing rate will be 500 kilograms per day, and the dispensing option will be 700 bar cascade dispensing. I'll select mid for the production volume, and I'll click to run the model. To view the results, I'll go to the results summary sheet, and I'm going to copy over the cost by function results table to a separate workbook for comparison with later scenarios. The total cost for this tube trailer distribution scenario is $5.84 per kilogram of delivered hydrogen. In the second scenario, I'll generate results using the liquid H2 distribution mode. The pathway represented in this scenario would involve gaseous hydrogen transmitted via pipeline to a terminal, where the gaseous hydrogen would be liquefied, then distributed using liquid hydrogen trucks. I'll leave my original selections the same, but I'll choose liquid H2 as the distribution mode. And because the hydrogen will be in a different state, I have to choose a new dispensing option, so I'll select 700 bar gas via pump. Then I'll run the model. From the results summary sheet, I'll copy over the cost by function results to my comparison workbook. The total cost for the liquid H2 distribution scenario is $7.82 per kilogram of delivered hydrogen. That's about a third higher than the same result for tube trailer distribution, almost $2 more per kilogram. I'll dig into some more granular differences in a minute, but I first want to run one more scenario. I'll now generate results using the pipeline distribution mode. The pathway represented in this scenario would involve gaseous hydrogen transmitted via pipeline to a distribution network of pipelines that deliver the hydrogen to a refueling station. Similar to before, I'll leave my original selections the same, but change the distribution mode to pipeline, and I'll have to choose a new dispensing option, so I'll select 700 bar cascade dispensing. Then I'll run the model. From the results summary sheet, I'll copy over the latest cost by function results to my comparison workbook. The total cost for the pipeline distribution scenario is $7.86 per kilogram of delivered hydrogen, which is quite close to the total cost for liquid H2 distribution, and again about a third higher than the cost for tube trailer distribution. Now, to look more closely at the results from these differing distribution mode scenarios, I collected the cost breakdown results, which are in the first table on the results summary sheet in HDSAM, and arranged them in the same worksheet in my comparison workbook to line up some of the delivery processes. The first two processes deal with pipeline transmission. No surprise that these results are all basically the same because I selected the pipeline transmission mode in each scenario. For the two gaseous hydrogen distribution scenarios, tube trailer and pipeline, there is some cost for geologic storage. We can see that costs are the same between the two scenarios. For the liquid hydrogen distribution scenario, there's a process for hydrogen liquefaction. The cost to convert hydrogen gas into liquid hydrogen is almost 40% of the total hydrogen delivery cost. For the intermodal scenarios, there's a terminal process where the hydrogen is processed for distribution either by tube trailers or liquid tankers after liquefaction. The cost at the terminal is higher in the tube trailer scenario than the liquid H2 scenario. The pipeline distribution scenario doesn't have a terminal for mode switching because the gaseous hydrogen would flow from a transmission pipeline to distribution pipelines. The last two processes in each scenario involve the costs to distribute the fuel and the costs of the refueling station. In the tube trailer and liquid truck scenarios, the distribution cost is under $1 per kilogram of hydrogen. In the pipeline scenario, the cost is $3 per kilogram, and the majority of that cost is in the capital required for the pipeline distribution network. The range of refueling station costs across the scenarios is smaller than in the distribution costs. The tube trailer scenario refueling station costs are the lowest, the pipeline costs are the highest. In each scenario, the refueling station costs are 40 to 50% of the total hydrogen delivery costs, a substantial portion. I've left some questions unanswered in this video, like why the terminal cost is higher in the tube trailer scenario than the liquid hydrogen scenario, and what is contributing to the differences in the costs for the refueling station across the scenarios. You can dig into the formulas and the results if you want to explore these finer scale questions, but I'm going to leave it there for this video. If you want, you can view more videos about Argonne National Lab's Hydrogen Model Suite on the Hydrogen Model YouTube channel. That's it for now. Thanks for watching.